Thank you. Very good. So Zoltán will talk today about the parallelization of single qubit gates with bichromatic driving. So far, at least I see you're still your PowerPoint, like program, not the presentation mode, but maybe.
I think you should be able to see it now, but.
I see that you pressed the button, it looked like it, but it didn't switch for me to.
Can't you see it now?
No, I don't see any.
Sorry, I will try to do something.
Now I see the first slide.
Sorry, I'm just not really familiar with Zoom.
No problem. Usually it works right away when you use, when you don't use multiple screens, then I had issues. So.
Yeah, I mean, we can see your screen, but you have to go to the slide mode. Then we can see the full screen. Yeah.
But it seemed like to me that Zoltán pushed the presentation mode button on the lower right and nothing changed. So that might be.
Is it okay now?
We again see the PowerPoint. We don't see the presentation mode. Now it starts again. Yeah, now it's working.
Okay, sorry for.
No problem. We are anyway good in time.
Okay.
Yeah.
So hello everyone. Thank you for the introduction and also for the opportunity to talk here. My name is Zoltán György. I'm an undergraduate student from Eötvös University, Budapest, Hungary, and this is a joint work with Gábor Széchenyi, who is also from the Eötvös University, and with András A from Budapest University of Technology and Economics. This project was started as a QIntern 2021 project, and we just finished it. So I will talk about the addressing of spin qubits arranged in a crossbar architecture. So these black circles and this gray ellipse represent spin qubits. So we have here 9 spin qubits arranged in a crossbar architecture like this, and our goal is to manipulate the state of the qubit. It means that we want to induce an oscillation between the qubit 0 and 1 state. And it can be achieved by some external driving field. And what we do here is that we use bichromatic driving. So we use 2 different AC electric fields with omega and omega bar frequencies. And these 2 frequencies are in the same order of magnitude. These are the plunger gates that are required for the addressing of qubits. And the important statement here is that this oscillation, this addressing of qubits is possible only if the sum of these 2 frequencies is equal to the splitting frequency of the qubit. And it makes possible selective addressing of qubits because the addressing requires the presence of both electric fields. So either one of the 2 fields only is not enough. So in this concrete example, only this qubit at the center will be addressed because this is the only one that feels both electric fields. This is another setup that was proposed by experimental physicists. It has a same idea behind it. It's just a bit more experimentally feasible. But our work was inspired by this setup. So let's talk about the exact spin qubit that we are using, which is the so-called flopping mode spin qubit. This qubit was proposed in 2019, and it was demonstrated experimentally, also described theoretically, but the monochromatic driving of it when it is driven by a single monochromatic electric field what we do here is that we drive this qubit with bichromatic driving with 2 different electric fields. So what is a flopping mode spin qubit? Flopping mode spin qubit is basically just an electron with a spin degree of freedom confined in a double quantum dot. A quantum dot is just an electron trap, an artificial atom, if you like. Here you can see the confinement potential of this double quantum dot. And if we put 1 electron in the system, it can be hybridized between these 2 dots. We can create Rabi oscillation between the qubit 0 and 1 states if we apply a homogeneous magnetic field. We also need some effect that connects the spin degree of freedom with the position of the electron. In our cases, it is a spin orbit interaction, which makes possible spin-dependent tunneling of the electron. Here we choose the qubit 0 state to be roughly the spin down state, and the qubit 1 state to be roughly the spin up state. Here you can see a Rabi oscillation. A Rabi oscillation is a really simple oscillation described by this formula. Pt is the probability as the function of time that we will find the electron in the qubit 1 state if it was initially in the 0 state. And if we measure the state of the electron at some maximum of this oscillation, we get Pauli X gate. So this is the model Hamiltonian that we used. It is pretty simple. It has some parameters. This T0 parameter is the tunneling amplitude. The epsilon parameter describes the potential energy difference between the 2 confinement potentials of the quantum dots. It is also called on-site energy or detuning. This omega z parameter is the well-known Zeeman splitting term, while we also enable the 2 quantum dots to have different g factors, and this is described by this delta omega z, and I will refer to this as just g factor antisymmetry. This omega vector is the spin orbit interaction. It has an x, y, and z component. This sigma vector is formed by sigma x, sigma y, sigma z Pauli operators that act on the spin subspace, while these tau y, tau 3, tau 1, tau z matrices are also Pauli matrices, but they act on charge subspace. Spin subspace means that the basis states of that subspace is spin down and spin up state, while the basis states of charge subspace is that the state that means that the electron is in this left dot or in that right dot. Here are the 4 energy levels of the flopping mode spin qubit. These are labeled by their dominant charge and spin state component, and we use the lowest 2 energy states as the states of the basis states of the qubit. So we use the charge ground spin down state and the charge ground spin up state. There's an energy difference between these two levels, and there is a splitting frequency which corresponds to this energy difference. We managed to give a perturbative formula for the splitting frequency. We can see that it is dominated by the Zeeman splitting, but also the G factor antisymmetry and the spin orbit interaction have some contribution. So about the bichromatic driving, this is the term of the Hamiltonian that describes the bichromatic driving of the flopping mode spin qubit. Here is the omega and omega bar frequencies. We can also have some initial phases, and this EAC and EAC bar are the electric field strengths. This is the precise resonance condition. Resonance condition means that if this condition is met, then we will have a coherent, perfect Rabi oscillation. Which is the interesting thing here is that the sum of the 2 driving frequencies has to be equal to the splitting frequency of the qubit, but we also have to add some correction to this. which is the Bloch-Siegert shift, and it depends on the strengths of the driving fields. And as we will see later, this Bloch-Siegert correction is in some cases relevant, and it must be taken into account. What are the roles of these initial phases? They just mean that if we start from the qubit 0 state and we do this bichromatic driving, then we will do a rotation on the Bloch sphere, and the initial phases determine the axis of rotation. Here is a perturbative result for the Rabi frequency, for the bichromatic Rabi frequency. It is only valid in the weak driving regime when the driving strengths of the electric fields are small compared to the qubit splitting. As you can see, the Rabi frequency is proportional to both of these electric field strengths. So it is second order in the electric field, and it is also proportional to the spin orbit interaction. So we can say that a bichromatic Rabi oscillation is slower than a monochromatic one, because a monochromatic Rabi frequency contains only one electric field strength. Here is the Rabi frequency plotted as a function of qubit detuning. We can see here that at zero detuning, Rabi frequency is 0, so we don't really have an oscillation. And at some non-zero finite detuning, we have a maximal Rabi frequency. Here is a Rabi frequency as a function of one of the two driving frequencies, because we know that the sum of the driving frequencies has to be fixed, but we have some freedom there. We can choose one of the two frequencies as we like. As you can see here, the higher the difference between the driving frequencies, the higher is the Rabi frequency. We determined the Bloch-Siegert shift. This is also a perturbative result. It is second order in the electric fields, so it is in the same order of magnitude as the frequency of the oscillation. It is proportional to the G-factor antisymmetry. It means that if in the presence of G-factor antisymmetry, the Bloch-Siegert shift is important and it is not negligible. It must be taken into account. This is just a Bloch-Siegert frequency as a function of this electric field strength, and we can see here a nice parabola as we expect from this formula. We took into account also the effect of the harmful effect of the charge noise. Charge noise is one of the most important noises which can cause the decay of the oscillations. Charge noise is basically just a random electric fluctuation, the fluctuation of the detuning of this epsilon parameter. Because it is a random fluctuation, we cannot follow this fluctuation with the driving frequencies, so it causes the shift of the resonance, and we will drive the qubit off resonantly, which will result in a damped oscillation. Here we assume that the detuning is quasi-static and has a normal distribution. Quasi-static means that we do measurement rounds, we do more measurements, and under the duration of one measurement, this epsilon is constant, but it can change between the measurements. So we will end up with expected or average oscillation, which can be given by this formula. Here, PT epsilon is the probability that we will find the qubit in the one state. It also depends on the epsilon. Here you can see 3 different Rabi oscillations. This blue oscillation is a perfect oscillation without charge noise. This red one contains charge noise but doesn't contain G-factor antisymmetry, while this black one contains both of them. As you can see, relatively small noise, because it is relatively small noise, causes a significant drop the oscillation. And if we have G-factor antisymmetry, it reduces more. So the conclusion here is that we should try to minimize the charge noise and the G-factor antisymmetry. So let's talk about the application, because I have talked enough about the disadvantages of the bichromatic driving. Let's talk about the advantages. One of the advantages that I have talked about already is the selective addressing. So this is our setup that is more realistic. Here, these circles are quantum dots. These gray barriers allow hybridization of one electron between these two, or it can be said for every pair, a hybridization of electron is possible. And these black barriers separate these pairs of quantum dots from each other. So if we put electrons in these pairs, we will end up with separate flopping mode spin qubits. The driving of flopping mode spin qubits is possible with these diagonal plunger gates if we apply AC electric fields on it. And the idea behind the driving is the same. It is just a more realistic setup. And the most important thing is the parallelization of single qubit operation. So let's assume that we have an n times n qubit grid arranged in a square-like architecture, and we need two times n different driving frequencies to achieve a complete parallelization of these single qubit gates. We have to connect different frequencies on n different rows. And an important thing is that we need frequency multiplexing on the vertical lines. So every single vertical line, we have to add n different driving frequencies. And if these conditions are met, so if every frequencies are in pairs, and if they are resonant, so omega I plus omega I bar is equal to omega split. For example, omega 1 plus omega 1 bar has to give omega split, so they have to be resonant, so they can drive this qubit. But another important condition is that two frequencies from different pairs cannot be resonant because it would mean that this qubit would be driven also by this omega 2 bar and omega 1 frequencies. So what we say here is that this harmful crosstalk can be easily avoided because the bichromatic resonance is pretty sharp. So it means that if I choose this omega 1 and omega 1 bar to be resonant, I can choose this omega 2 bar to be very close to this omega 1 bar and still not be resonant to this qubit with omega 1. And so it makes possible having a very high resolution in frequency. And if we have a high resolution of frequency, then we can have a relatively large number of qubits without significant crosstalk. And using the initial phases of these pulses on the vertical lines and also the duration of the pulses, we can achieve any single qubit gate on this n times n qubit grid. So in conclusion, we found that bichromatic Rabi frequencies are lower than the monochromatic ones, and this is the most important disadvantage of bichromatic driving. Another interesting thing is that the Rabi frequency has a maximum at a non-zero detuning, because in the case of monochromatic driving, it has a maximum at zero detuning. And we should try to minimize the G-factor antisymmetry because it causes Bloch-Siegert shift and also increases the harmful effect of the charge noise. And we presented the advantage and the most important application of bichromatic driving and this arrangement in a crossbar architecture, the parallelization of single qubit gates, which is possible if we use frequency multiplexing. Thank you for your attention, and I will gladly answer the questions.
Thank you very much, Zoltán, for this nice presentation. It was really interesting. I think because it's not my field, I think I learned a lot, and I actually have a question, but let's first see if the audience has a question. There's nothing in the chat here. I don't know about Discord. It doesn't work on my computer.
I cannot see any questions here, so maybe you can go ahead. Yeah.
Then I will ask my question to Zoltán. So you you said that you don't want to have the crosstalk between the different qubits, right? So you pick the frequencies correct, which is of course nice. That's sometimes what you want. But could you also turn that around and say, I want this crosstalk to have 2 qubit interactions? Is there, or maybe it's not my field and I don't know, but could you also use this architecture to essentially couple 2 qubits and then entangle them or something like that?
I mean, yes, we didn't think about this enough, but it is certainly an advantage and of the crossbar architecture that the qubits are next to each other. I mean, if the qubits are aligned in a line or in one dimension, then one qubit has only 2 neighboring qubits. In the case of a crossbar architecture, we have 4 neighbors. So neighbors are of course important if we want to have 2 qubit gates. So that's why crossbar architecture is promising. But I can't tell you if this crosstalk can be used for 2 qubit gates or not, but it is an interesting question.
Okay, thank you. Very nice. Okay.
Okay, so I'll just stop the recording. Yeah.
Okay.